All right, so we're back. We're computing the MLE, where we're computing the MLE for a PMF on a finite set. And here's our expression for the MLE. It's this constrained maximization problem. We're maximizing over these thetas, maximizing this expression. And we did some calculations, and we figured out that maximizing that thing, so the argmax of the original expression, which is theta MLE, is also the argmax of this expression here. The constrained maximization. And that's equal to this. So let's start playing with this some more. So let's introduce a little bit simpler notation for these things. Let's call, I don't know, Q sub j nj divided by n. Now, I claim that this is a probability. This is also a PMF, this Q thing here, and in other words, that the sum is 1. Because if we sum over j, if we sum the nj's over j, then we get, well, maybe it's easier here. If we sum nj was this this quantity, this sum by definition, and if we sum this over j's, we could switch the sums, move the sum over j inside, and every xi is equal to j for some j, and only one j, so that's just 1. And then we're summing from as I goes from 1 to n, so we get n. And therefore, the sum of the nj's is n, and so the sum of the qj's is 1. Okay, so that was just verifying that this is in fact a PMF on this set. So we can rewrite this thing as sum from j goes from 1 to m, qj log theta j. And now this equals, so I'm going to try to make this look like, so if you know what entropy is, then you probably know what relative entropy is, or maybe you know what relative entropy is. And I'm going to try to, so my plan here, where we're going with this is, I'm going to try to use the fact that for relative entropy, I'll use theta and q since we're using theta and q. The relative entropy between two distributions is always non-negative. I may have these switched, but we'll see what happens. So relative entropy between two distributions is always non-negative, and my plan is to use that to somehow show that this is a maximum. I'm not sure how this is going to work, so we'll see what happens. So let's try to make this look like relative entropy. Well, what's relative entropy? Relative entropy is, right, let me put it over here for a between two distributions. Let's say, actually I think I want this to be q with theta. It's the sum, I'll do it over j since that's what we're working with, from 1 to m over all the values of the distribution, the distribution, all the different elements that this is a PMF over. Qj log qj divided by theta j. So this is relative entropy, and it's always non-negative. And also, right, a key fact is it's equal to 0 if and only if these are equal. These distributions are equal. So to make this look like relative entropy, we need to, what do we need to do? We need to, it's going to be maybe minus relative entropy. So let's subtract. So this is qj log, I'm running out of room, theta j, we can divide by, so let's make it theta j divided by qj. I'm going to put a minus to fix the fact that these are upside down. and then plus qj log qj, the sum over j's. So this is true because the log of the ratio, this is log of theta j minus log of qj, so that cancels. You distribute the qj's, then you move the sum in, that cancels. So this equals minus, this is minus the relative entropy of q with theta minus the entropy of q. Okay. Now we wanted to maximize this thing. Ah, right. Okay. Now things are looking good. I think we might have it. Okay, so we wanted to maximize this thing. Hopefully that was clear, right? Yeah, I think that's clear. So, but you can check that step if you are unsure. We want to maximize this thing. Okay. So let's start to write it out here. So the argmax, let's see. Theta MLE was the argmax of the probability of our data given theta such that the sum of the thetas is 1. That was equal to the argmax of this thing, 1 over n log probability of the data given theta. And this equals argmax of this guy, because that's equal to that, but this doesn't depend on theta, right? So that's just the same as maximizing this part, or minimizing minus that. So that's equal to argmin of the relative entropy between q and theta. And the relative entropy between q and theta is always non-negative, and it's equal to 0. Let me write that. Relative entropy between q and theta equals 0 if and only if q is identically equal to theta. So every element is equal. So that means to minimize this, we can make it 0 if we choose theta equal to q, right? We're minimizing over thetas. We can make it equal if we choose theta equal to q, but we can't get any lower than that because relative entropy is always non-negative. So that means that this argmin equals q. That's it. Equals q. And so that means we have our result. So that means theta MLE, that thing, is q, and q is, well, let's just write out what it is. Q is this thing. It's the nj's divided by the n, but by n. So this is n1 over n, n2 over n, etc., up to nm over n. And this has a very natural interpretation, since each of these nj's here is the number of i's, the number of xi's that are equal to j. Then each of these qi's here, or these qj's rather, it's the fraction of points, a fraction of x's that we get that are equal to j, which we sometimes refer to as the empirical probability that x equals j. So this is just the empirical distribution. Given empirical means, given our data. So it's the MLE is just the empirical distribution on this finite set. So it's just sort of the most natural thing that you would do, right? If you were if you had, think back to our example with the die, you're rolling the die, and you want to estimate what's the probability that this die comes up 1. Well, what would you do? The most natural thing to do might be, well, just roll it a bunch of times, count how many times you get 1, that's n1, and then divide by the total number of times that you rolled it, and that's n. So you just look at the fraction of times that the die comes up 1, and that is your maximum likelihood estimate for the probability. Remember, you're estimating the probability that x equals 1. So this is a nice case where it's not too difficult to compute the MLE. We use this little bit maybe non-intuitive route using the relative entropy, but it wasn't too hard once we sort of saw how to go, and it has a very, very natural interpretation as this empirical distribution.